We'll now look at the idea of square roots and radicals. This symbol right here means the square root of a, and we just read this as the square root of a. And we specifically need to be a greater than or equal to 0, meaning we cannot take the square root of a negative number. The square root of a is equal to b whenever b squared is equal to a. Once again, b is also greater than or equal to 0. So the idea is when I'm taking the square root, I want to know what number squared gives me this. Let's look at some examples. The square root of 36. The square root of 36 is equal to 6, since we know that 6 squared is equal to 36. If I want to try to do the square root of 81, that would be equal to 9, since 9 squared is equal to 81. On the other hand, if I want to look at the square root of negative 49, this does not exist. So we specifically said we could only take the square root of a positive number, and this is negative. And this is because there is no number that when I square it, I get negative 49. 7 squared is positive 49, and if I do negative 7 times negative 7 is also positive 49. We can expand on this idea of square roots as well. The nth root of a is equal to b whenever b to the n is equal to a. So instead of squaring, we can look for any power. If I want to look at something like the cube root of 27, that would be equal to 3, since 3 cubed is equal to 27. If I want to do something like the fourth root of 16, this would be equal to 2, because 2 to the fourth is equal to 16. The cube root of negative 64 is equal to negative 4, because negative 4 cubed is negative 64. So it is possible to take some higher roots of negative numbers, in particular when that degree is odd. The fact that this was the cube root allowed me to take the negative. If I would have been taking the fourth root, I would not have been allowed this negative sign. Let's look at some basic properties of these kind of roots. The first one, the nth root of a times b is equal to the nth root of a times the nth root of b. So essentially I can break a root up over multiplication. Similarly, I can break it up over division. The nth root of a over b is the nth root of a over the nth root of b. So I can actually use multiplication and division to break up my roots. If I try to take a root of a root, I multiply those roots. So the mth root of the nth root of a is equal to the mnth root of a. I have that the nth root of a to the n is equal to a whenever n is odd. So if that number n is odd, my root and my power will cancel each other out. And the nth root of a to the n is equal to the absolute value of a if n is even. For our purposes, I'm going to assume that all of my variables are going to be positive, so I don't have to worry about the square root, and I'll be able to just take these two and condense it down to say the nth root and the nth power are going to cancel each other out. So let's look at some examples on using these properties. Let's start with one with just numbers, the square root of 96. There is no number that when I square it, I get 96. So we might start thinking about how we can rewrite this as a multiplication. You might realize that it's 8 times 12. However, I also can't take the square root of either 8 or 12. So let's keep breaking it down and seeing what we can get. I know that 8 is 4 times 2, and 12 is 2 times 6. And now I can start to see things that I can take the square root of. I'm going to rewrite this as 4 times 4 times 6, since I know what the square root of 4 is. I can then use those properties of roots to break this up as the square root of 4 times the square root of 4 times 6. We know the square root of 4 is 2, so this becomes 2 times the square root of 6, which is 4 root 6. Now let's do one that has some variables in it. I want to look at the square root of 50x to the 5th. And I'm going to break this up the same way. Let's start with the 50. I know that the 50 is 25 times 2. And now I need to deal with the x to the fifth. Since I'm taking a square root, I'm going to want x squared, because a square root and a square cancel each other out. So I'm going to rewrite this x to the fifth in terms of x squared. So we write it as x squared times x, since when we add these exponents, we get back to x to the fifth. I can use that property that says I can break these up over multiplication. So now I have the square root of 25 times the square root of 2 times the square root of x squared times the square root of x squared times the square root of x. And then I can start simplifying things that I know. I know the square root of 25 is 5. I don't really know anything about the square root of 2. I know that a square root and a square cancel each other out, so the square root of x squared is x. And then I have another one of those, the square root of x squared is x. And then the last thing I can't simplify at all, it's just the square root of x. Since the order of multiplication doesn't matter, I'm going to rearrange this and write it as 5x squared times the square root of 2 times the square root of x. And the same property that allowed me to break this up into multiple roots also allows me to combine things. So this is 5x squared times the square root of 2x. Now let's do the cube root of x to the 7th. Before, when I rewrote my x, I rewrote it as x squared because I was taking a square root. The fact that I have a third root this time means I want to write this in terms of x cubed. So I have the cube root of x cubed. I've accounted for 3 of my 7 x's. I can write another x cubed. That gets me up to 6 of my 7 x's. So I have one more left, which we'll just write as x. We can then use our property to break this up. That gives me the cube root of x cubed times the cube root of x cubed times the cube root of x. A root and the power are going to cancel each other out if they're the same index. So the cube root of 3 and x cubed will cancel down to just an x. That leaves me with an x for the first term and x for the second, and then I have a cube root of x at the end, which I don't know what to do with. And then I can write this as x squared times the cube root of x, and it's as simplified as we can get it. I now want to do the fourth root of 16x to the fourth y to the 8th. Since I'm dealing with the fourth root, I want to write things in powers of 4. My x is already written as a power of 4, so I'm going to leave it as x to the fourth. And since 8 is 4 plus 4, I have that I can write y to the 8th as y to the fourth times y to the fourth. I can then break this up over multiplication. I have the fourth root of root 16 times the fourth root of x to the fourth times the fourth root of y to the fourth times the fourth root of y to the fourth. Since 2 to the fourth power is equal to 16, the fourth root of 16 is equal to 2. And then we can remember that powers and roots are going to cancel each other out. So the fourth root of x to the fourth is just x, and the fourth root of y to the fourth is just y. That leaves me with 2 times x times y, or 2xy squared. When dealing with radicals, one of the most common mistakes to make is to try to break up a root over addition. It is not true that the square root of a plus b is equal to the square root of a plus the square root of b. As an example, let's consider the square root of 9 plus 16. We know that 9 plus 16 is 25, so we have the square root of 25. And the square root of 25 is 5. On the other hand, if we try to break this up, the square root of 9 is 3, and the square root of 16 is 4, which would then add to be 7. And these are definitely not equal, so make sure you do not break a square root up over addition. The next thing I want to look at is actually adding roots. And in order to do this, since we can't just combine them, we need to actually try to simplify them first. So let's start with the square root of 45. We know that 45 is 9 times 5, which we can break up as the square root of 9 times the square root of 5. And we know the square root of 9 is 3. So that term becomes 3 square root 5. Now let's think about 405. 405 might be a lot harder to break up, but the fact that it ends in a 5 at the very least means it's divisible by 5. In fact, it's 81 times 5. I can then break that one up as the square root of 81 times the square root of 5. And we know the square root of 81 is 9. And now, since they both have a square root of 5 term, we can just add the coefficients. We can add the numbers in front. And when we do, we get 12 root 5. The next one I want to look at is the square root of 36y minus the square root of y to the 5th. Since I'm taking a square root, I want to break that y to the 5th up in terms of y squared, which would be y squared times y, since now I still have 5 y's there in that second root. I can then break these up. That would give me the square root of 36 times the square root of y minus the square root of y squared, square root of y squared, square root of y. I know the square root of 36 is 6, and I don't know the square root of y, so that's just going to stay as the square root of y. The square root of y squared is y, since the root and the exponent cancel each other out. So I have y times root y. And we can actually factor out a square root of y to give us 6 minus y squared all times root y.